Welcome, and today's lecture of in digital control systems we will be looking into this root locus method and the design of digital control systems in using root locus method. And root locus method is a method which is used to find the or analyze the stability of a system. We have various methods that are already in literature to study the stability analysis, out of which this root locus method is a time domain method. We have frequency domain methods also, which we will be discussing in our later classes. Right. And root locus method, in this root locus method, we will be first dealing with the location of poles in the S plane in continuous time systems or in the Z plane in the discrete time control systems. For example, let me go with a brief introduction with regards to, we will review the root locus method in the continuous time systems, just a gist of what root locus method is in continuous time method. In that we have seen an S plane, right, you have this axis sigma real axis and j omega the imaginary axis, and we try to locate the open loop poles and zeros. Open loop poles and zeros in the continuous time system, we try to locate those poles and zeros. For example, if we are having like this 4 poles where n is equal to 4 and m is equal to 2, here in this case we have 4 poles and 2 zeros, and we will try to locate for this we don't require any, by trial and error method also the root locus method can be obtained, but if there are a set of rules that are to be followed, so that it will make it easier for us to design the root locus in this S plane and hence determine the stability of the system, which means the gain of the system can be obtained by using this root locus method. So eventually, just without following any rules also, you can just have that at every pole you can say that k is 0. At every pole you have k0, and at every infinity k values. At every 0 of the system you have k is infinity. Here we are going to determine the stability using open loop poles and zeros. We don't require to go for closed loop poles and zeros. Eventually, but by using this closed loop, open loop poles and zeros, you can also determine the stability analysis of the closed loop control systems. Okay, so here the root locus branch will be starting from every pole and ending at every 0 or at infinity, right? At infinity along straight line asymptotes. The asymptotes are also starting on the real axis. They intersect. There may be different number of asymptotes for any given system. They will be starting on the real axis, and therefore the centroid is called the intersection of all these asymptotes, and where you can also have a point where you can find asymptotes based on the open loop poles and zeros of the given system, right? So here, for example, let me say there are 4 branches that are starting. Okay, the first thing which we'll have to see that is the root locus is symmetrical about the real axis. Therefore, you can also just draw the diagram on the upper half of the real axis, and you can just draw the mirror image of the upper half in the lower half of the real axis. Okay, and we should also be able to find out what is the portion of the real axis that is lying on the root locus. Portion of the real axis. Right. So the real axis, you can take some test point here somewhere, and you can see if you count the number of poles and zeros on the real axis, or because they are complex conjugate, you need not consider this because it will not give us any information, much of information. The poles and zeros on the real axis to the right of any test point which you consider may be considered, and then you can see that if their count is odd, then that point lies on the root locus. Now you can see if this is the test point 1, 2, 3 and 4, right, or 5 and 6. You have if you also count the complex conjugate poles, that is not an issue. right? You will get, and if you are getting an even number, then it is not lying on the real axis. Now let me see a test point in between these two zeros. You can see that you have to the right of that test point, you can see that we have three number of poles and zeros, right? So any point on this portion, if you look towards its right, the number of poles and zeros are odd, right? So this portion lies on the real axis. Okay. Now if I stand here and consider this is test point, it is again 2. So this portion is not lying, and here it is again lying on the real axis in between, lying on the root locus. So these are the. Now we will be having the branches of root locus starts from right, and this entire portion doesn't lie on the real axis, lie on the root locus. This entire region from minus infinity to this point 0 doesn't lie on the real axis. Therefore, these are the 2 points which are lying on the real axis. Now these 2 points, branches are starting here, because this can't be started here, and here also there is some branch that is starting. So here you can see, you can find out because they are poles, complex conjugate poles, you can find out the angle of departure. Right? If there are zeros as complex conjugate zeros, then it will have angle of arrival, because the root locus terminates at a 0. And here at a pole, the root locus starts at a pole. Therefore, when these two come and meet, as k is increased, the poles start moving, and when these two are at some point of value of k, they do meet each other, and since they are meeting each other, they will try to break away. Like this. Okay. At an angle of 90 degrees, plus or minus 180 by 2. Two number of poles are meeting. Therefore, this angle can be 90 degrees, plus 90 degrees and minus 90 degrees. So they are coming and meeting at this point, and you can say we will be having again these two coming and meeting here and trying to go and terminate. So this is called the break-in point, and this is called the break-away point. Okay. So this is what is happening in this, and here you can see there are, if for example if it is moving like this, it is also moving like this. For example, if you have any angle of departure also, you can have these values also like this, moving upwards along straight line asymptotes. You will have some asymptotes here, right? Along these straight line asymptotes, they will be moving. Okay. And you may be having only 2 asymptotes here. Okay. So this is what is known as root locus, a gist of root locus, and the same thing is applied in discrete time control systems, and we will see in detail what these are happening. Only thing, the change that is happening in discrete time control systems is this z-plane. That is, here imaginary axis is the point, but in z-plane, for discrete time control systems, you have real part of g of z and imaginary part of the function g of z. Okay, and you have a unit circle. This is called the unit circle. Now we already know that any point that is lying inside the unit circle contributes towards the stability of the system. On the unit circle will contribute to the marginal stability of the system, and any point lying outside the unit circle contributes to the instability of the system. Similarly, here in the S-plane, left half of S-plane, poles and zeros will contribute to the stability of the system. On the imaginary axis, instability, and marginally stable, and right half of S-plane, they are unstable poles and zeros. Right. So this is the only difference between the S plane and Z plane with regards to root locus method. Therefore, the same method that is used in continuous time system, the root locus method, can be directly applied or extended to the discrete time control systems. So let us see what is happening in this. So the relative stability, in fact, the relative stability is being observed or analyzed here in this Z plane in the using this root locus method, the relative stability based on the root locus plane poles and zeros. But here it is also important for us to find out the effect of poles and zeros when t is changed, when the sampling period t is changed. What are the effects of sampling changes in the stability when t is changed? So t must be as small as possible is what we have discussed earlier with regards to discrete time control systems, and t must be in such a way that the sampling frequency where omega s is equal to 1 by t, which is the sampling period, sampling frequency and sampling period, and omega s must be equal to greater than or equal to 2 times of the highest frequency component of the system. Therefore, with that, with sampling theorem in mind, we will go ahead with this. Right. So t must be as small as possible, so that sampling frequency will be as high as possible. Okay. So there are certain rules that we will have to follow to design this root locus method for any discrete time control systems, and due to which, based on these rules, we can design or draw a root locus technique like we have drawn in continuous time control systems. Okay. So we try and see what are the rules that we have. First thing, we will try to draw the block diagram of a closed loop control systems. It is nothing but we have G of Z, okay, and input R of Z, output C of Z, the feedback signal or feedback sensor, which we have H of Z, is represented in terms of H of Z. Now what is the closed loop transfer function here? C of Z by R of Z, it is nothing but G of Z by 1 plus G of Z into H of Z. Now the denominator of the transfer function determines the stability analysis, because we use this as the stability, this factor. Therefore, that is called the characteristic equation. Right, and this characteristic equation is given by f of z, which is equal to 1 plus g of z into h of z. And since they are continuously connected and there is no sampler in between, you can directly give it as 1 plus g into h of z. You can simply directly multiply these two factors. That is the only difference between these two. And when you equate this to 0, then it is a characteristic equation, and or otherwise it is a characteristic polynomial. Now based on this characteristic equation, we will try to see what is happening in the root locus method. Okay. So now you can see here, G of Z is the plant or a system, and H of Z is another transfer function, in fact, right, whose input is C of Z and output is some B of Z, let us say, right, some transfer function or feedback signal that we are going to get. Okay, so the combination, now this is a complex system, right, f of z is complex, therefore z can be given as, z can be substituted with z is equal to jv, z is equal to jv. In fact, you can find out the j and k of the system. For example, let us say, what is f of z? F of z is equal to, let me consider it in this way, f of z is equal to 1 plus gh of z can be given as k into z plus z1, z plus z2, z plus zm by z plus p1, z plus p2 z plus pn, where m is less than n, right? Zeros and all z's, zi's are zeros, I is from 1 to m, and all p's are poles and p is from 1 to n, where m is less than n. This is the condition which we will have to consider for considering the transfer function or characteristic equation of the system. So this is the rule 1 of the system. Rule 1 of the root locus method. Root locus method is to determine the characteristic equation of the given system. Right, G of z is the open loop transfer function and this is the closed loop transfer function. Okay, and in this what we can understand is you have 1 plus GHZ, 1 plus GH of z is equal to 0, is equal to 0. This is the closed loop characteristic equation. Closed loop characteristic equation. And therefore, what is GHZ? GH of z? GH of z is this part. If you add plus 1 to that, it's becoming a closed loop transfer. So this is your GH of z. It means that the open loop poles and closed loop poles are the same. Okay. And second point, the closed loop zeros are combination of closed loop poles plus open loop zeros. Closed loop poles, you can add these two, right? So if you take the LCM and get z plus p1, z plus p2, z plus pn plus k times of z plus z1, z plus z2. So this closed loop zeros, the numerator part determine the zeros, and the numerator part you will have zeros and poles. The closed loop poles and open loop zeros by the closed loop poles, right? So you have all the closed loop poles and open loop poles. Therefore, you can say that you can use open loop poles and zeros to determine the closed loop poles and closed loop stability. Closed loop stability analysis of closed loop control systems, discrete time or any system. Okay, so this is the first rule which we will have to consider. Rule 1, you will have to first determine the characteristic equation of the system and find the closed loop poles and zeros. So from there you can just locate on your z plane. Locate on your z plane. The z plane is this form. The real part and the imaginary part of f of z, and you can just locate the poles and zeros that were obtained using this characteristic equation. Once this characteristic equation is obtained, you can get the poles and zeros. So this first rule is finished. Once you have finished this, the second part or second rule which we will have to obtain is rule 2 of root locus method. In the rule 2, we will have to determine the number of open loop poles. We have determined number of open loop zeros. This is determined by m. This is n, and this is by m. And once these are obtained, you can say that when you have this, okay, z plane, real part of f of z and imaginary part of f of z, and you have the unit circle here, and for me, let us say we are having two poles here and a zero here. For example, we are having open loop 2 poles and open loop 1, 0. Okay, and with this, it is important for us to find out k is equal to 0 and k tends to infinity. That is, the root locus starts or originates at an open loop pole. Root locus starts or originates at an open loop pole where k is equal to 0 and the same root locus terminates or ends at an open loop 0 where k tends to infinity. But here there is one problem. If you have equal number of poles and zeros, then any root locus branch that starts at any pole ends at one particular 0. But I have two poles and one 0. It means one pole, at one pole the root locus will start and end at a 0, and the root locus branch that is originating at another pole, where will it end? It will end along an asymptote. It will end along an asymptote where k is also tending to infinity along straight line asymptote, you can say. Straight line asymptote. Right. So we have m number of branches originating at m open loop poles where k is equal to 0, and the remaining n minus m branches okay, just I'll try to finish this one, where there are m branches originating at m open loop poles, k is equal to 0, and terminates at open loop zeros where k tends to infinity. M open loop zeros where k tends to infinity. Now what are the remaining branches we have? We have n minus m branches, root locus branches. Right. These terminate at straight line along, you can say they are terminating along straight line asymptotes, right, where k tends to infinity. The straight line asymptotes also will be having some straight line asymptotes. Here you can simply have this as a both the poles start and meet here, and they tend to follow this semicircle, meet here, and one will go and terminate here, and the other will go and terminate along straight line asymptote. So minus 180 degree line is the straight line asymptote for this particular problem. Okay, hope this is understood, because I have two poles and one 0. There is one pole, that is m branch, there is one branch originating at open loop pole and terminating at open loop 0. Right, at pole k is 0 and at 0 k is infinity. Right, and the remaining branches, n minus m branches, they terminate along straight line asymptotes. This is the rule 2 of the system, of the root locus method. Hope this is understood. Now we shall go into the next part, rule 3. Rule 3 of the system tells us the point on the portion of the real axis of the z plane, the portion of the real axis of the z plane. Okay, this is your unit circle. Now we have again the same example. If I have considered, okay, or I can also consider some more poles and zeros. For example, let me say this is the poles and zeros that we have inside the unit circle. I am trying to take a stable system. Okay, now I want the rule 3 says what is the portion of the real axis? Portion of the real axis. The entire real axis doesn't lie on the root locus, right? The portion of the real axis that is lying on the root locus. Okay. So what is this one? We will have to find out. Take any test point. Consider any test point anywhere on the system. This is the real axis which is coming from minus infinity to 0 and 0 to plus infinity. Every complete real axis we will be considering from minus infinity to plus infinity, and take any test point from minus infinity till this value, till this is minus 1, isn't it, and this is plus 1, okay, and this is 0 here, okay, and let me say this is somewhere around minus 0.4, this is minus 1 plus j 0.8, sorry, minus 0.2 plus j, sorry, minus j 0.8. For example, we have this thing. This is minus plus 0.4. For example, just a consideration like this. Okay, angles also can be considered, right? Anything can be considered here. That is not an issue because it is a z plane, which is a complex quantity. You have real axis and imaginary axis, and angle and magnitude also can be considered here. Okay, so you are considering a test point here and looking towards its right of the test point, you count the number of poles and zeros. If they are odd, then that point lies on the that point on the real axis lies on the root locus. Okay, so 1, 2, 3, 4, 5, 6. So anywhere you consider a test point from minus infinity till minus 1, just before minus 1, this entire real axis will not be like a portion of the real axis from minus infinity to minus 1 up to minus 1 will not lie on the real axis because the number of poles and zeros are not odd, they are even in number. And now in between consider a test point between minus 1 and plus 0.4. Now when I consider here 1, 2, 3, 4, 5, you have odd number. So this is the portion until this value that is lying on the real axis, which is a part of the root locus. Now consider from here to here, plus 0.4 to minus 0.4. This is plus 4 minus 0.4. Okay. Now in between these values, what are the number of you can say this need not be considered here, and you have odd number. Therefore, this also doesn't lie in the real axis. And from here, at any point of this, if I stand, I have 1. 1 is an odd number. Therefore, this also lies on the real axis. Now, this is what we are going to see. So, on the real axis, and anywhere here I stand, there are no poles and zeros, so it is not considered. Okay, so I have minus 1 to minus 0.4 plus 0.4 to 1 as the root locus. Portions on the real axis lying on the root locus. Okay, so rule 3 states that the portion of the real axis that is lying on the root locus is determined by any test point to the right of which there should be odd number of poles and zeros, right? And that is considered, and you will be getting this rule 3. Okay, so we will be going and saying into the rule 4 of the system. Okay, now rule 4. Rule 4 is you can determine the asymptotes. Okay, now what are the asymptotes of the system? Asymptotes are nothing but you can consider to be angles. Angles of asymptotes can be considered where phi A is equal to plus or minus 180 degree into 2q plus 1 by n minus m, where n is the number of open loop poles, m is the number of open loop zeros, and q is 0, 1, 2, 3, so on. This asymptotes angular momentum can be up to infinity, but whatever are required only we will be considering. Okay. So 180 degree into 2q plus 1 by n minus m. And therefore, after finding this asymptotes, it is necessary for us to find out the rule 5 gives us the centroid. Centroid of the asymptotes. Centroid of asymptotes. That is, the asymptotes, where do they meet? Asymptotes, where do they meet? Right. There are a lot of asymptotes that are coming into picture. Now let us say n minus m is equal to 2. Now when you consider q as 0, what is this? 180 into 0 plus 180 by 2 plus or minus 90 degrees. Now when q is equal to 1, so 2 plus 1 is 3 into 180 by 2. So 90 into 3 is plus or minus 270 degrees. Okay. Now when q is equal to 2, that is 5 into 90 plus or minus 450 degrees. Okay. Now when q is equal to 3, what is it? Right. Q is equal to 3, 2 into the 7 into 90, 60 plus or minus 630 degrees, and this keeps on going. Now let us see what is plus 90 degree minus 90 degree. Okay. Plus 270 degree. What is plus 270 degree? This is plus 270 degree when you are considering like this. Okay. And minus 270 degree when you are considering like this. Minus 270 degrees. It is, you are considering like this. Again plus 450 degrees. It is this one. Minus 450 degrees. Plus 630. So you are having the same value. So you need not require, but you need not find out so many things. You can find out just only these values. Okay, so you will be having those asymptotes and you will be discussing that, and this should be the, if your real part and imaginary part are here, and this can be called as the centroid of the system. And centroid of the system can be obtained by sigma A, because it should obviously be lying on the negative part of the real axis. If you are going for continuous time control systems, negative part is always contributing to the stability. Maximum the poles and zeros, we will be trying them to be pushed towards the stable region, that is which is lying on the left half of S plane. We consider these values. That is not at all an issue. You can also consider this m minus comes here. Now what is sigma? Sum of all poles minus sum of all zeros by n minus f. Sum of all open loop poles minus sum of all open loop zeros by n minus m. Negative sign will be staying there. Okay, so you will be having this value centroid. The centroid is given at this. And the angle of asymptotes are given like this. Centroid of asymptotes, angle of asymptotes. These are rules 4 and 5. Okay. Once we have determined these values, you can see how the remaining branches of root locus that are trying to follow the straight line asymptotes can be obtained. Now we can also see, for a better example, I will try to give you one more. When n minus m is 3. When n minus m is 3, what is this? 180 by 3 is plus or minus 60 degrees into q is 0, you have 1. Again, plus or minus 60 degree. When q is 1, it is 3. And plus or minus 60 degrees into q is 2, it is 4 plus 1, 5 into 60. Right. So this is plus or minus 60, plus or minus 180, plus or minus 300. Consider only plus signs. You can say plus 60, plus 180 and plus 300. Otherwise consider all negative values. You have minus 60, minus 180 and minus. For example, let me say this is the centroid which is lying on the left half of S plane or imaginary axis or Z plane. You can say 60 degrees is this line. You can draw a dotted graph. dotted straight line plus 60 degree, and again this is plus 180 degree, this is the line. Okay, minus 180 degree line or plus 180 degree line, and plus 300 degree line. 300 degree line should be like this, because if you are considering it like this, this is 300 degree line. Okay, so you have three different asymptotes here. So they will try to follow the straight line asymptotes, which must be followed if in case there are any number of branches which do not terminate at any open loop 0, which are originating from open loop pole, right, which we have discussed in the rule 2. Okay, so this is these are rules 4 and 5. Okay, so this is understood, and we will go into the rule 6 of the system of the root locus method. Rule 6 gives us some information about the breakaway point and break-in point. Breakaway point and break-in point. Now this is again a simple system. This is a plane, and okay, the unit circle, the real axis and the imaginary axis which we have. For example, let us say we are having some poles, 2 poles here and 2 zeros here. Okay. Breakaway point is the point where any number of poles meet and break away, right? Because from poles when k is equal to 0, as k is increased from 0 towards infinity, what is happening? The poles start moving. The poles start moving towards each other on the real axis, right? And at some point of time they will try to meet each other, but their destination is to meet at 0, right? They cannot stop here. Therefore, what they will do? They will take a different route. Right, both will meet each other and they will turn their directions, and that is the angle with which they are breaking away or breaking in is determined by plus or minus 180 degree by r. Now how many r indicates number of branches that are meeting, right? So these two are the branches that are meeting, and here r is equal to 2 plus or minus 90 degrees. So around 90 degree line they are meeting, plus or minus, plus 90 and minus 90. Once they are there, what is happening? They are trying to be pushed towards any 0, and in the system we have 2 zeros. We have 2 zeros here. So what they try to do? They will try to move towards, as k is increased, they will try to move towards the zeros, but they don't directly go there, right? They meet here. And so this is called break-in point. This is called the break-away point. Right. When they meet here and they move towards infinity. Right. So they meet here, break away, meet here, break in. Break in and move towards the zeros. So these are called breakaway and break-in points. Now it is very important for us to find out these 2 points. What is this one? How to find? Okay, how to find these 2 points? We have a simple rule, simple formula to find out. Now let us say we are going into the characteristic equation of the system now again. Right, to find out the break-away and break-in point, what we try to do is we try to find out 1 plus f of z is equal to 1 plus g h of z. Okay, and this is equal to 0. Let me say we have this, we have again k into some function b of z by a of z is what we have, right? These zeros z plus z1, z plus z2, z plus zm by z plus p1, z plus p2, z plus pm, that I have represented as b of z by a of z. Right. When I equate this to 0, what is this k that we get? Minus a of z by b of z. Okay. Now we have this. Now to find that value, dk by dz is equal to 0. Dk by dz is equal to 0. If you consider this equation, what do you get? We have b square of z, right, and b of z. The negative sign is as it is, minus sign, I have left it as it is, b of z into a dash of z minus a of z into b dash of z. B dash or a dash is d by dz of a of z, or d by dz of b of z. Okay. Now from this, if I equate this to 0, what do I get? I get some values, right? Those values can be obtained. Now because k is eliminated from this and you get some value of z, right? If you are having two values of z, for example, if you are having k is some plus or minus some 0.7, let us say, right? If k value, sorry, z value is plus or minus 0.7. This, if I have only one value, only breakaway point, and I don't have any breaking point, then I can consider only one value. But that value, because this is a real value, this 2 points, right? For example, if I am having these values like this and minus 0.7, if it is lying here and that is a portion of the real axis, then only I will consider that as the breakaway point, because in between any two poles there should be somehow some breakaway point. Between any two zeros there should be some break-in point. That is what is considered here. But logically you can understand, because two branches come and meet and go towards 0. Meeting here is very, very easy for the points to meet at this point and break in. Here they should break away. They should meet and break away. Right. So breakaway point, breaking point. At between any two poles, you can have breakaway point. Between any two zeros, you can have break-in point. Okay. So finding out the breakaway point and breaking point is our rule 6. Now let us consider rule 7. Rule 7 is to find out the angle of departure and angle of arrival. Rule 7. Angle of departure at complex pole and angle of arrival at complex 0. Now let us say if the poles and zeros are not lying in the real axis, they are lying on the space, right, on the two-dimensional space, then they are complex conjugate. You have two poles which are complex conjugate and two zeros which are complex conjugate. Let us say I have two poles here. Okay. Now what is the angle of departure? At a pole, k is equal to 0. And we know that the pole, at any pole, open loop pole, a root locus branch must originate, right? And these two are mirror images. So we can only consider one value, right? The other thing can be mirror image. So you need not consider this. Okay. When you have one value like this on the space, then automatically there is a complex conjugate value for that. Then we need not consider for that. We can study only for one pole. Now how to find out the angle of departure at an open loop pole? Now let us consider the remaining poles and zeros. Okay. Now find the angles. Let me say theta 1. What is the angle with this one? This is theta 2. This should be equal to 90 degrees. And this is theta 3. Now consider all this anti-clockwise direction to be positive. Okay. Phi 1. Okay. the angle contributions at any zero must be given as phi's, and angle contribution by any poles, by other poles, because I want the angle of departure at this value. Therefore, I want from other poles and zeros. So, angle contributions. So, this is this one. So, then theta A, okay, that is angle of departure. Theta A is angle of departure, is nothing but 180 degree minus of theta 1, sum of all angle contributions of all poles at this pole. So, theta 1, theta 2, theta 3 minus sum of all angle contributions of all zeros at this pole minus phi 1. So, this is your angle of departure. Okay. So, angle of departure at any complex pole is obtained. Similarly, angle of arrival also can be obtained. So, this is rule 7. Rule 7. And now we will see the last rule and the ultimate rule, rule 8, which is nothing but determining the gain K at any closed loop pole. For example, if you are having your root locus like this, any root locus of this form, and from here to somewhere up to infinity. Okay, this is my root locus. Now, any point on this root locus can necessarily be called as closed loop pole. Okay, so what is the value of gain K at such value Z? Okay, at this value Z, what is the value of gain K is what is to be determined here. So, to determine the value of gain K, you can find out the value here. Okay, using this, and that is nothing but, you can say K is product of gains or gain products, gains from all poles by product of gains from all zeros. Okay, that can be termed as 1 by K. Okay, or K can be reversed. Okay, so this is the design based on root locus method. You have all these things to be, and gain K is always considered to be positive. It can never be negative because it is starting from 0 to infinity. As K is increased from 0 to infinity, the root locus can change its values, and hence closed loop poles locations also can be varied. Therefore, for range of K, the range of K for which the system can be stable can be determined using this root locus method, right? Because if the values of Z changes here from here to here, right? Values of Z changes, and when these changes, what happens? There is some range of K. K is 0 here, and at this value some finite value. K is some finite value. So during this way, we don't want the value of gain K from 0 to infinity. We want for a particular range of K, because we are working on physical systems, and these physical systems cannot be infinitely used, because there are every limitation for every system and every physical system. Therefore, you require only finite values, and hence the range of K can be determined using this root locus method for the system, closed loop system, to be stable using open loop poles and zeros. Okay.